Okay, we're going to switch gears just a little bit here and talk about horizontal and vertical tangents. As you can see, it says horizontal tangents to a parametric curve occur when dy dt equals 0. You can see that if you have a curve that kind of comes up like this, let's say, and you have a horizontal tangent right here, where this arrow is pointing to, that makes sense that dy dt would have to be 0 because the curve isn't rising or falling there, so y isn't growing or shrinking, hence dy dt is 0. Same thing down here in blue. Let's say you have a curve that's coming like this. Obviously, it wouldn't be a function because it's failing the vertical line test. But right here at this point where the arrow is pointing to, you have a vertical tangent because x is not going to the right or the left. It's not growing or shrinking. So dx dt, the rate of change of x, is 0. Now, if dx dt and dy dt are both 0, then you can't assume it's a horizontal or vertical tangent. That's a different case. So you have to make sure that one of them is 0 and the other is not. Okay, let's see what I mean with a good example. Example 8 says find all points of horizontal and vertical tangency to the curve. And there may not be any. We'll start with the horizontal. Remember, for the horizontal tangent, dy dt has to be 0. So let's see what dy dt is. Dy dt, or my y equals equation, is going to be 3t squared. If you set that equal to 0, it follows that t is 0. And if t is 0 and you plug that back into both of these equations, x and y are both 0. Which means that at the point 0, 0, the origin, you have a horizontal tangent. Okay, now let's get the vertical tangents. Obviously, in this case, we want dx dt to be 0. dx dt, if you take the derivative up here, would be 4 minus 4t. You set that equal to 0 and you solve it. T will come out to be 1. And of course, if t is 1 and you go ahead and plug them back into these blue equations, you can see that x will be 4 minus 2, so x is going to be 2. And y is going to be 1, because 1 to the third is still 1. And so you have a vertical tangent at the point 2, 1. I was curious to see if our answers were actually correct, so I went ahead and got my TI-84 and graphed the original equation in parametric mode, and now I'm going to see what the graph looks like. There it is. You can see that at 0, 0, we've got a horizontal tangent, and at the point 2, 1 right here, where my mouse is, that's a vertical tangent. So those are correct answers. Very cool. All right, on to the next. Okay, here again, we're going to find all the points where we have horizontal tangents and vertical tangents to the curve. It's a parametric curve. We'll start with our horizontal first. Okay, for the horizontal tangents, dy dt, of course, has to be 0. And I found that dy dt is 4 cos theta. If you set that equal to 0, then cosine of theta is 0. So then theta has two possibilities. It could either be pi over 2 or 3 pi over 2. If theta is pi over 2, and I plug pi over 2 back into both original black equations, I get x is 2 plus 3 cos of pi over 2, which would be 3 times 0. That's going to make 2. If I try the y, I'm going to get negative 3 plus 4, but now we're taking the sine of pi over 2, which is 1. And that's going to make negative 3 plus 4, which is 1. And so one point where we have a horizontal tangent is the point 2, 1. That's if theta is pi over 2. But what if theta is 3 pi over 2? Again, we can plug that in to see what happens. Again, for the x, you're going to have x equals 2 plus 3, again, an instant replay, times 0, so that will also be 2. But with the y, that's going to go a little differently. If you plug the y in, you're going to have negative 3 plus 4 times, but this time it's going to be negative 1 because you're doing the sine at 270. So that will be negative 7. And so that's going to give you the point 2 comma negative 7. So this shape has its horizontal tangents at 2, 1, and 2, negative 7. And now we'll try out the vertical tangents. As we know with the vertical tangents, dx dt has to be 0. And dx dt is going to be negative 3 sine theta. We'll set that equal to 0. So that means that sine of theta is also 0, which means that theta is 0, or theta can also be pi, because sine of pi is 0. Let's say that theta is 0. We'll go with that first. If that's the case, then you have x is 2 plus 3 times 1. We know it's 1 because, again, cosine of 0 is 1. That'll make 5. And then y, in this case, should be negative 3 plus 4 times 0, because sine of 0 is 0. That's going to end up being negative 3. So the point 5 comma negative 3 is one of the places where you're going to have a vertical tangent. What if theta was pi? Let's come up here. See what we have. Starting with the x, it's going to be 2 plus 3, but the cosine of pi is negative 1. So really that's 2 minus 3. That's going to be negative 1. For the y, you're going to have negative 3 plus 4, and that's going to be sine of theta. But again, sine of theta is 0. So that's just negative 3. And so your other point will be negative 1, negative 3. And so your vertical tangents will be at those two locations. So 5, negative 3, negative 1, negative 3. And oh, by the way, this parametric pair ends up making an ellipse when you graph it. I just wanted to see if my answers were right. And by gosh, the vertices and covertices of the ellipse happen to be exactly where I figured they would be. The horizontal tangents are in red, the verticals are in the blue. And wow, it worked. All right, one more thing to tell you about, and it's right here. Arc length can be done in parametric form as well as just regular rectangular form. Back in Chapter 7, we learned the arc length formula, and it looked a lot like what we have now, except that back in Chapter 7, this was just a 1, and this was dy dx getting squared. Because we only had a y and an x, we didn't have that third variable, that parameter. Now, since we do, we convert the formula to this. When you think about it, it has a Pythagorean theorem look. And in fact, back in Chapter 7, when this still was 1, 1 is a perfect square. It happens to be 1 squared. So this isn't really all that different. It's just that we have all three variables. So let's say we wanted to know how long this curve, y equals x squared, was from the point 0, 0 to 3, 9. Of course, it's a parabola, so it's going to go up like that. And before I do this, let's say that it was a straight line. Let's say it was just a nice, boring straight line, like so. You can tell that the red line is going to be shorter in length than the green curve, just because the curve is like a sagging, telephone wire. It's going to have some slack. It's going to take up more space. If you just go with the red, you can imagine a right triangle here. This side would be a length of 9. This would be 3. Based on the point 39. You could do Pythagorean theorem and get 3 squared plus 9 squared equals c squared. And c would be the square root of 90. All right, so we know that the green is going to be longer than the square root of 90. Just in case you were wondering, the square root of 90 is 9.487. Okay, so instead we'll find the length of the green curve. We can do that using our brand new formula. Okay, the arc length, usually we call it L, is equal to the integral from 0 to 3. We're going to use the x-axis here. It's going to be a large square root. We have to take dx dt and dy dt and figure out what they are. Well, first, before I do that, I have to turn this into a parametric look. Right now, it's just y equals x squared. Since we only have two variables, sometimes you can sort of finesse or trick the calculator into going into parametric if you want to. I'll just call y equals t squared, and I'll just say that x equals t. And that way I still have this equation, but now I've made it parametric. All right, so let's start over here, dx dt getting squared. Well, dx dt is simply going to be 1, and you square it, and it's still a 1. Plus dy dt. Well, dy dt is 2t, and when you square the 2t, you get 4t squared. And that's dt. Now, you cannot do that by hand. There's no way to u-sub it. You just can't. So you use the calculator, you plug it in, and it comes out that L is 9.747. And that is a completely believable answer, because remember, we said that the curve is going to be a little bit longer than this 9.487, and it is. It's 9.747, so that makes complete sense. But you can see that the formula from before works parametrically as well. We're going to try one more example, and then we'll call it quits for section 10.1, a 2-day lesson. Okay, let's find the arc length. Before we start, we're going to go ahead and take a look at this x. I'm going to rewrite this. That's actually going to be 2t to the half. I think that'll be a little easier. And so therefore, dx dt is just simply going to be t to the negative half power. All right, obviously dy dt is extremely easy. Dy dt is simply 1. And we can find the length. The length is going to be the integral from 1 to 3. These limits of integration should never be mysterious. We have to tell you where we want you to stop and end. Otherwise, you don't know what the length is going to be. There's no way to solve it. Big square root, and you just take these items and put them in. So we're going to take t to the negative half. We're going to square it. We're going to take this 1. Now, by the way, you don't always have a 1 as one of the numbers. It just happened to occur that way. This will turn, for what it's worth, this will turn into just t to the negative first plus 1, still under a square root. And again, you just have to put it in your calculator. And the arc length will turn out to be 2.485. That's how you find arc length with parametrics. There's only 2 more sections to go in BC, and we'll be done learning for the year. So great job, everybody. Take care.